Hello and welcome to this presentation of our SMDB paper entitled Towards a Benchmark for Learned Systems. I'm Laurent. This is joint work with Andreas, Ryan, and Tim from MIT, as well as Umar from Microsoft Research. So recently, data management systems have undergone a paradigm shift with the introduction of machine learning to automatically specialize systems to a specific situation, a specific workload, a specific data set, and so on. Now, these new learned systems can adapt at runtime to changes and leverage specific characteristics of the workload to gain significant performance benefits. So several learned systems take different approaches. To cite a few, we can synthesize optimized data structures or components, we can help existing components perform better, or even automatically learn the best configuration knobs for a given scenario. Now, the ultimate goal of this approach is for one day to have a database that automatically instantiates all of its components and tunes their interaction at runtime to have a truly instance-optimized system. Now, while learned systems have already shown in the lab that they can achieve orders of magnitude performance improvements, and they can also adapt much better than traditional systems to changes in their environment, it remains largely unclear how well these numbers will hold in more realistic production environments. So currently, evaluating learned systems is pretty challenging. For instance, learned systems are intrinsically capable of specializing very effectively to a given data set and workload. And that makes it kind of difficult to quantify how well a learned system will perform if you only evaluate it with fixed data and workloads that are just too easy to learn. For similar reasons, it is also not enough to just measure a learned system's average performance, as these average values, they just hide too much information about what actually happens over time. Now, a learned system can also very easily overfit to a benchmark, which makes it really hard to evaluate how well it will work in the wild. Of course, we also need to account for the training time, the training cost of the underlying machine learning techniques that are used. And finally, although the research area is quite young, there are a few different approaches and wide-ranging designs that make it difficult to perform adequate comparisons. So in order to address these challenges, we're going to need a few things. First, we're going to need to have realistic and ideally hard to predict data sets and workloads. We're also going to need new metrics to capture adaptability, specialization, and so on. Finally, we're going to need to be able to measure and compare system costs with human costs, such as, for example, the cost of a DBA. Now, we believe that the best way to provide a better understanding of learned systems is by creating a new benchmark that specifically targets these systems. And currently, there doesn't happen to be any such benchmark. Now, having such a benchmark would provide insights into the characteristics of learned systems, including how good a given system is at adapting to changing situation, or how well it can specialize to a given situation. It would also facilitate comparisons across systems based on somewhat more empirical evidence. And finally, having such a benchmark could also help address concerns about worst-case performance of learned systems, for example, if the benchmark were to include adversarial workloads. Now, one important thing that I really want to clarify is we're not trying to replace existing benchmarks. We want to add a new benchmark to complement these benchmarks. So in this talk, we will first go through some background on traditional benchmarks and discuss the limitations, particularly in the context of learned systems. Next, I'll present our initial ideas for what such a new benchmark could look like, in particular with respect to the configuration and execution, the workload, the data, as well as new metrics. And finally, we'll briefly conclude. So let's start with traditional benchmarks and why they're not good enough to really understand the performance of learned systems. So traditional benchmarks like TPCC, TPCH, and so on, as well as YCSB, measure a system end-to-end using a synthetic workload and report its average performance. Now, unfortunately, this is just not good enough for learned systems. The average performance does not give you enough information. Of course, these benchmarks also tend to forbid leveraging workload knowledge, which is fundamentally incompatible with a learned system. As I said before, we don't want to replace traditional benchmark results. These results are still relevant, they're still important, but we need to adapt the benchmark and kind of try to go beyond these metrics. So let's look at these issues in more details. So I've already hinted previously at the first limitation of traditional benchmarks. Fixed workloads are just, unfortunately, they're just too predictable and therefore they're just too easy for learned systems. Similarly, it's pretty easy to overfit to a fixed data distribution. So overall, this has two consequences. First, learned systems have a bit of an unfair advantage when you compare them with traditional systems. And second, the results are probably not going to be particularly interesting as they will not tell you why it is better or where it is not as good, right? They'll just give you an average number and that's it. So ideally, we'd like to have a benchmark that exhibits a wide range of behaviors during a single execution run. And it should have transitions to different workloads and data distributions. It's also important that the benchmark captures the behavior of the system during these transitions, as that will provide useful information about how well the system is able to adapt. Now, the second limitation of traditional benchmarks is that they focus on average metrics. So although this may be good enough if the data and workload are fixed, it's just not sufficient when we want to understand how well a learned system can adapt to different scenarios. The average numbers are just too coarse-grained. In particular, it doesn't really make sense to compare two learned systems based on their average performance. For example, take the two systems at the bottom of this slide and their throughput over time that are represented here. So both systems achieve the same average throughput, like 5 queries per second in this case. But System A provides a much more consistent performance, whereas System B just suffers from a sharp drop in the middle of the execution. Now, which of the two systems is the best at adapting? Like it's already not an easy question to answer, but if you only have the average throughput, there's just not enough information to answer. Another limitation of traditional benchmark has to do with model training, right? So a traditional benchmark typically initializes the system, loads the data before it starts executing the benchmark for, let's say, a given amount of time or a given number of queries. And then it reports the performance for the entire execution. Now, clearly, this does not work very well with learned systems because they require training. And ideally, this training effort should be accounted for separately. In particular, it would be good to understand how much training is required, how much overhead the training process introduces into the system. It would also be nice if we were able to characterize how efficient the system is at training. So finally, the last limitation I want to talk about is related to total cost of ownership, or TCO. Now, traditional benchmarks generally include a total cost of ownership, which is a dollar value estimate of the total expenditures involved in running a particular system for like a specific duration. However, at least in the research community, as we all know, we tend not to care too much about the total cost of ownership. Now, this sort of begs the question of what to do with systems whose fundamental value proposition is at least in a big part to reduce the cost. Now, one thing is for sure, obviously we can't ignore the cost anymore. In fact, we would like ideally to compare the cost of developing and training a learned system with human cost, say for example, the cost of a DBA. So beyond that, there's even a question of how to estimate the TCO of a learned system, as it may require, for example, special training, special hardware, or if the system requires supervised learning, then you may need to collect and curate labeled datasets. So now we can start thinking about what this new benchmark could look like. Again, in this paper, we are focusing on some preliminary ideas. So in terms of the configuration options, the new benchmark should of course support the traditional configuration options like the scale factor, mixes of query streams, and so on. It should also support learning-specific configuration. So in particular, there should be settings to configure different workloads and data distributions, as well as the mix of the two. And we should also make the transition duration between these workloads and data distributions configurable. And of course, we should allow for possible retraining of the models in between. Now, finally, the benchmark should also provide an interface to report the training time or the training overhead so that this information can later be incorporated into the results. So in terms of execution, we envision something which is quite similar to traditional benchmarks. So you'd have one or more drivers that are running on separate machines that are connected to the system using a fast network. So perhaps more so than for traditional benchmarks, our learned benchmark has a clear need for high-quality data sets and workloads that represent as much as possible real-world conditions. Now, of course, short of having access to such data sets, which is pretty hard, we propose two approaches that can also be used in complement to try and get us at least part of the way there. Now, the first approach would be to provide guidelines for selecting databases and workloads. For example, the benchmark could include a software tool that evaluates the quality and relevance of a given data set to the benchmark. This tool could, for example, attribute low marks to uniform data distributions and workloads, while favoring data sets that exhibit high skew or varying query load. Now, the second approach would rely on synthetic data and workload generation. So this is more ambitious, right? But we may be able to actually synthesize high fidelity workloads and databases using a combination of privacy preserving techniques and machine learning. And this would really be nice to have. So one idea that seems interesting is to deploy the benchmark as a cloud service. Now, this benchmark as a service could really be useful with a few things. First, it would make it really easy to evaluate different systems in a unified environment. Second, it may be a good opportunity to execute real-world workloads and datasets that are not publicly available. And finally, it could also be interesting to include holdout workloads that the system is only allowed to execute on, but is not allowed to use for training. And for example, this would make it easy to measure out-of-sample performance. So in practical terms, this benchmark as a service could complement the benchmark results. For example, we could require a system to run in the cloud benchmark in order to be included in the official benchmark results. And we would be happy to host that for the community. Now, finally, we propose some metrics for benchmarking learned systems. So the goal of these metrics is to complement average performance results by trying to capture dynamic behavior and providing more details regarding specialization, adaptability, training, and so on. So here in particular, I'll focus on 4 metrics. So the first metric is a breakdown of throughput for different workloads and data distributions. We propose to report descriptive statistics, here using a box plot, for each combination of workload and data distribution. So our goal with this is to more precisely capture the specialization and adaptation capabilities of a learned system. Here we have example results, like this is not from a real system, this is an example of what this plot could look like. And so on the y-axis, you have the throughput, the x-axis, you have different combinations of workloads and data. And you have this SPI function that measures how far workloads and data distributions differ from each other. Now, basically, the idea with this is that the similarity values are less important than the actual order in which these different workloads and data distribution come in. So as long as we can sort the x-axis by similarity, the plot should make sense. Like you would go left to right, and you would have more and more dissimilar situations. Now, a plot like this could be used to evaluate, for example, how well a system adapts and manages to maintain a stable throughput as the workloads and data distributions change. This could also be useful to report out-of-sample performance, for example, by plotting holdout distributions alongside the baseline. Now, here's the second metric that we propose to include in the new benchmark. We plot the total number of queries executed over time, so this is cumulative, and we do that for several systems. So like in this case, the slope of the curve would correspond to the throughput. And this plot is actually useful because a learned system may experience significant throughput variations due to changes in the workload of data. It provides a good visualization of just how adaptive a learned system really is. So here in particular, it's quite easy to see that the learned system, which is in red, starts out slow, but eventually catches up to the traditional system, which is in this blue dashed line, and eventually it performs better. And we can also use these plots to derive a single value metric by computing the area difference between a learned system and an ideal system that has a fixed constant throughput. Or we could also compute the area difference between 2 learned systems, either over the entire execution or for a given time interval. Now, the third metric is service level agreement violations. So here we report query latency bands at 1 second or 10-second intervals throughout the execution. Right? And each query latency band represents the number of completed queries within an interval. So in other words, it represents the throughput because the y-axis is the number of queries completing during that time interval. Now we then split the band into 2 categories depending on whether the query finished within the allotted SLA time. And we color the bar green or red accordingly. Now, such metrics are often used in monitoring systems, and they provide quick visual information about changing behavior. And we think it could also be really useful here. So for example, imagine you have a change in the workload or data distribution, and then you can look at the size of the red bars and the overall number of queries executed within each time interval to indicate how fast the system is able to adapt. Now, to push this further, we may even wish to increase the number of bands and like color code them. For example, you could have like green, yellow, orange, red, and so on to have more details. So the last metric for our new benchmark is throughput per cost. Now in this figure, the x-axis represents the cost of the system and the y-axis corresponds to the average throughput that is achieved at that cost. Now we plot a traditional system in blue here, whose cost is kind of a step function corresponding, for instance, to the cost of manual optimization by a database administrator. Now, of course, in reality, this could look very different for different systems and different kinds of optimizations, right? This is just an example. And we compare this blue line with the throughput per cost of a learned system, which we represent here in red. So here, the learned system throughput is more of a curve shape, right? But this is, again, only just an example. And so we think that this plot can provide some interesting information with respect to the cost of each system. For example, it could be that it's more profitable to use a learned system with a GPU rather than to rely on manual system optimization by a DBA. In particular, we could also derive a pretty interesting metric from this plot, which is the training cost to outperform a traditional system. And this would be where these two lines meet, right? Okay. So to conclude, I've presented our work towards building a new benchmark for learned systems. We strongly believe that mainstream adoption of learned systems will require convincing practitioners and companies alike that the benefits of these systems are just too significant to ignore. We think the best way, or at least one of the ways to address various concerns about learned systems is through better benchmarking. So this is why in this paper we presented some preliminary ideas, and we also identified some key challenges that will need to be solved in order to build such a benchmark. Of course, our next step, which we're currently working on, is to actually build such a benchmark and see how well various systems perform using it. Now, on that topic, we welcome any input from the community, and we hope to see more research work done in that area in the near future. And with this, I'm signing off. Thanks for watching. Bye.